Hi there, this is arrangements and permutations for the A-level Further Maths Discrete course. It's actually a very similar video to one I've done for statistics. And if you're doing statistics, you may find you don't need to do this again. A bit like my exercise 1B.1, 2, 3, and 4, all the same. 5 actually is different. But if you're not doing statistics and say you're doing mechanics and decision, discrete module, then this will effectively be very much needed. And there are questions in the exams, on the OCR A Further Maths exams, which basically need you to know this stuff. And you might have picked some of this up elsewhere, but you might not have done. So let's have a go. Look, we're looking at arrangements and permutations. Very often they use this word in the exam. They'll say, how many different arrangements are there of these 5 people? And if it is just 5 people like this, we saw in the last exercise, there would just be 5 factorial ways of arranging 5 people. 5 factorial is basically 120. And so that would be the end of the matter. But sometimes we want more than just simple arrangements. Sometimes we want permutations. And a permutation is where, yes, I want to arrange people, but I might have, say, 5 of them, but I have only got 3 chairs. So only 3 people come to dinner. And then you can see I've got a choice as to who I'm going to select, or technically to arrange in these positions. And just be slightly aware that if I've got, for instance, I've chosen to invite, well, what have I got here? I've got a teacher, I've got a nurse, I've got a artist, a magician, and Superman. Now I could choose to invite any of those 5 people, and it may well be I've chosen to invite the artist, the magician, and Superman. They look the most interesting, I think to myself. But interestingly, if I sit them in that order, that is different. This is a different permutation to having Superman, then the artist, then the magician. Although they're the same 3 people, and I've ignored the other 2 people, both exactly the same, the order matters. So I'm just going to write here, the order matters on these permutations. The order matters. And you do get questions when you look at it and you think it doesn't matter. And there's questions when the order definitely does matter. It might be, for instance, it's where you finish in a race. Coming first or coming third would matter. So just be aware of that. So let's have a look at some questions. Note, by the way, we've got a calculator button that does this. It's NPR. Have a look on yours. I think on mine it's above, on the Casio calculators, the old Carl Ask Whiz. It's above the times, and it says NPR. Above the divide, incidentally, it says NCR, and we need both of those 2 things at a variety of times. Now, on the newer Class Whiz, you have to press, I think, the tools button or something. You'll need to find out how to do it and Google it if need be. Depends which calculator you've got, of course. But notice there's also this formula. We saw what factorial notation was last time. If I had, for instance, 8 things that I wanted to arrange, but I only have room for, say, 4 of them. 5 of them would be a better number to use, I think. And then I would just calculate this as 8 factorial divided by, notice, I then do 8 take away 5, which is 3 factorial. And I tap that into my calculator, and then whatever it says, I would do. I've got an example here. I've got 4 arrangements, number of arrangements of 4 items, sorry, when I've got 11 of them. Now that is given by, not surprisingly, 11p4. So I've written 11p4. Now, using the formula, it's 11 factorial divided by 7 factorial. But notice you can also think this is 11 times 10 times 9 times 8, because that's effectively what dividing by the 7 factorial does. And the answer apparently is 7,920. Okay, so if we're doing that, let's bear that in mind all the time, that we've got these arrangements and permutations from now on. And sure enough, here my first example is about people running the race. We've got 5 people running the race. In how many different ways can they finish? Look, I've not said anything about only selecting 3, 4, 5 of them, whatever it is. It's how many different ways can these 5 people finish in the race? And we've seen already from our previous work that that is what you do, 5 factorial. And I've already said that is equal to 120. So there it is, 120. This question, though, we've got these same people running a race, but now I'm going to give medals out. And because I'm a bit tight, I've decided only to give 2 medals. And how many different ways could I give out the gold medal and the silver medal? Perhaps I lost the bronze medal on my way to the event. But you see, I've only got 2 medals, so how many different ways can I do it? Well, effectively, I've got to permutate is the posh way to say it, but I've got to arrange 2 of them out of the 5. And the way I'm going to do that is 5p2. Now, using my formula, remember, it's 5 factorial. And then I take away 1 from the other, and that's 3 factorial. 5 take away 2 is 3. And 5 factorial I know is 1, which the 3 factorial gives me 20. Now, notice there's nothing wrong just typing that into your calculator, 5p2, and letting the calculator tell you it's 20, and just writing down 20. That's more than acceptable. So a few questions in this exercise here. How many different ways of arranging 6 items, etc. Look, you might want to pause the video. I'm just going to do them, but if you pause the video, then you can check your answers against mine afterwards. So anyway, I've got 6 items, so that's 6 factorial. That's 720. 12 items. Oh, I haven't even got a calculator next to me here, so I've or did I write this down before? Oh, I think I may have done. Yeah, it's a big old number. 12 factorial. 479001600, and we'll see if I've written that down right. But you can see it doesn't matter if there's 6 items or 29 items. You just chuck it in the calculator, it'll work. Find the number of different ways of arranging 6 items from a list of it. Now this is 8p6. I've got 8 of them. Notice, by the way, this is where I was always taught to write the p. So you might see it like that, or you might just see it with a normal capital P. But 8p6, that is 8 factorial divided by 2 factorial. And again, I'm just using my sheet here. According to me, it's 20,160. But again, that's something you would type into your calculator and get the answer. And find the number of different ways of arranging 3 items from a list of 12. Again, it's 12. I'll do a normal p this time to show it doesn't really matter for these days. 12p3, because I only want 3 of them. So that would be 12 factorial divided by 9 factorial. You can notice the subtraction that goes on that. And I get 13. Have I written that right? 12 items on the list. Well, I'm going to see what the answer is. I get 1320, but I'm not sure if that's right. Oh, it is, yeah. I just wrote it slightly wrong here. But that's now perfect. I like that. The other ones I'm hoping I did write down correctly. Okay, so I've got slightly different questions now, and the idea of this is to make you think about this more deeply. How many different words can be made from the letters A, B, C, D, E, which start from the letter A? So if you think about this on A, I've got 5 spaces to fill in my word, and it's got to start with the letter A. Now, by definition, that's done. It's definitely there. So I've got B, C, D, E left. And the way of organizing that is 4 factorial, because there's kind of almost that part of it is done and dusted. It's got to start with an A. 4 factorial equals 24. Only 4 letters left, effectively. B, how many different words can be made from the letters A, B, C, D, E? So there's 6 letters, which end with the letter F. So it's exactly the same idea. 3, 4, 5. I've got 6 now, but their end box is an F. So effectively, I've only got 5 letters left. You can arrange those 5 factorial ways. I'm allowed to take them all. So 5 factorial is 120. What about C? What does C say? And how many different words can be made from the letters A, B, C, D, E? Okay. Oh, which start from the letter A. So I've got an A at the front and end with the letter E. So there's not many choices, actually. I've got that going on. There's only 3 letters to put in the middle. I've got to use all of them. 3 factorial. And 3 factorial is 6. And then D, what does D say? How many different words can be made from the letters A, B, C, D, E, which start and end with the letters A and F either way round? All right, and so it can be A, 1, 2, 3, 4, and then the F. That's 6 letters in total. A, B, C, D, E, F. Yeah, I've done that right. And presumably it's 4 factorial ways of arranging them. But, and this is a but, because it can be the other way around. So it could be F at the front. 2, 3, 4, A. And you might think, well, this is the same. Well, it kind of is. Apart from those words will be definitely different from these. So I've got 4 factorial and 4 factorial. I reckon that's 24. Now remember, or means plus. Saw that last time. 48 ways of doing that. Let's see if my answers were right. 24, 126, and 48. Good, good, good. An additional question. Oh, look, this is when you get people sat around on the table in a circle, effectively. So A, B, C, D, E might be one way they sit. And just be conscious of the fact that if I was to put the E up there and the A there, and the B there and the C there and the D there, really it's still A, B, C, D, E going round. So they are considered the same. And because of that, you end up with a slightly different formula. In a circle, if you get an inner circle question, it's not n factorial, it becomes n minus 1 factorial. So using that fact, if you like, I've got 5 people for part A, it's going to be 4 factorial equals 24. What does B say? B says A, B, C, D, E. Okay, exactly the same. But A, B are married and want to sit next to each other. Now, when you do this, I always treat A, B as one person. That's one person. They're not one person. I wouldn't like to imply that at all. C, D, E. But what it means is really I've only got 4 groupings, if you like, around that table. And we know we've got to do n minus 1 factorial. So this is really like 3 factorial. Arranged around this circle. But bear in mind, it could be that, or it could be BA, and they could be a bit sneaky on us and just sit the other way around. So I've got to double up that answer. 3 factorial of 6 times 2 is 12. And I got 12, and I got 24. And I got one more set of questions for you. I've got 6 people. A, B, C, D, E, and F now in a straight line. So we're back to a straight line. 1, 2, 3, 4, 5, 6. And a B and C have to sit next to each other. So it's exactly the same then. So really, I can treat this B and C as just one person. And the other people, A, D, E, F, as 3, 4 more. But notice because I'm treating B, C as one person, really that's like 5 factorial. There's one less person. But again, they can be sneaky on us. They can switch the other way around. So I double it. 5 factorial is 120. So if I do 120 times 2, I get 240. Okay. And then, I don't know why this has appeared. I'll just worry about that later. And that's part 1. And then part 2, it says KLMNO. Again, they were in a straight line. K must sit at one of the 2 ends. Oh, right. So K could be there. But just be aware. K could decide to sit, because it says one of the 2 ends could decide to sit at the other end. L and M must sit next to each other. Perhaps they like each other. Perhaps, again, they might be married, like the last example, or just, for whatever reasons. But they've got to sit together. So L and M are one person. We treat them as one person. And I've only got then, I think, an N and an O left over. So really, this is, I've got 3 factorial. In fact, is it not 3? Yes, I've got it. That's it. 1, 2. I've got 3 people that I care about there. And this, I need to be slightly aware that L and M could go either way around. So that's 2 lots of 3 factorial. And this at this end, we've got L and M again sitting together, but we've got N and O. They're one person. 1, 2, 3. 3 factorial. But again, L and M can be sneaky, switch the other way around. And then we get in this. And effectively, we've got 2 lots of 2 times 3 factorial. What's 3 factorial? 6 times 2 is 12. We've got 12 dependent on each end, which way around it goes. I think it's 24. Let's see what I got when I last did this. 24 as well, 240 as well. Good. Look, so as I said, you might find that this is very similar to some of the work you've done already, but for those of you who are not doing statistics, you definitely need to see this. You will see exam questions on this. So this eventually will lead into exercise 1B, but there is an exercise 1B.1, 1B.2, this one, 1B.3, 4, and there's also a brand new one which doesn't appear on the statistics module, which is called derangements, which is 1B.5, and discrete people definitely need to see that. So all the best, and I hope you have, wish you the best, good luck in your exams. So thank you.